Hello, this is the section 3.8 lesson. In this section we introduce an extremely important theorem called the central limit theorem. The importance of this theorem cannot be overstated. Much of what we do in the rest of this book is based on the central limit theorem. Central limit theorem also has some interesting practical applications which are not terribly difficult to calculate. So we're going to start off with a few definitions here. First of all, many of our random experiments that we've seen before dealt with choosing a set of items from a larger set of items. And so in situations like this, when a set of objects is selected from a larger set of objects, the larger set is generically called the population, and the smaller set is called the sample. And then the number of objects in the sample is called the sample size. We're going to see these terms population, sample, sample size come up a lot, especially starting in section or chapter 4. Now, the central limit theorem deals with a specific random variable that we call the sample mean. And so here we're going to define this random variable, the sample mean. So it says if x1, x2 up to xn are mutually independent random variables that have the same distribution, then the random variable, we're going to denote it x bar sub n, and it equals the sum of these n random variables divided by n is called the sample mean. Okay? Now we're going to hear this term sample mean come up in chapter 4, and you maybe have heard it in everyday language. But this is maybe a little bit different than what you've heard it used in everyday language. This is a random variable that we call the sample mean. And so to illustrate what this random variable is, let's look at this example. So let's let capital X denote the weight in pounds of a randomly chosen 1 pound package of shredded cheddar cheese. Now I put 1 pound in quotes because not every package is going to weigh exactly 1 pound. The exact weight of a package is a random variable. Okay, so let's suppose we randomly choose 5 such packages, and let's let the random variable x1 denote the weight of the first package, x2 denote the weight of the second package, x3 the weight of the third, so on and so forth. So these 5 random variables, x1 up through x5, are really the same as x. It's just that x1 deals with just the first package that we choose. x2 is just the second package. Okay? So then these random variables, these 5 random variables, are mutually independent. Because we randomly choose 5 packages, the value of one package does not affect the weight of any other. So they're mutually independent, and they have the same distribution as x. In fact, they're really the exact same thing as x. It's just that x1 deals with the first package, whereas x2 is with the second, and so on and so forth. Okay. So then the sample mean associated with this scenario is the random variable denoted x bar sub 5, and it's x1 up through x5. We add those up and divide by 5. So that's all there is to this sample mean. Okay, let's suppose that we go out and we choose 5 packages and weigh each, and their 5 weights are shown right here. Okay. So these 5 weights are observed values of the variables x1 through x5. This is an observed value of x1, this is an observed value of x2, observed value of x3, so on and so forth. Okay. So now, to calculate the observed value of the sample mean, all we have to do is add up those 5 observed values of x1 through x5 and divide by 5. We do that arithmetic and we get the number 1.0508. Okay. So that is an observed value of this random variable x bar sub 5. And we're going to denote it with this symbol, simply lowercase x bar. We're going to not put the subscript 5 on it. Okay. So there we go. X bar, lowercase x bar, is an observed value of this random variable we call the sample mean. Okay. Now, this variable x bar sub 5 is a random variable. The central limit theorem tells us what we need to know about the distribution of this variable. Okay, so the central limit theorem says that if we have n mutually independent random variables with a common distribution, mean mu, variance sigma squared, then as n, the sample size, approaches infinity, the distribution of the sample mean, and this is the same sample mean that we just defined earlier, approaches a normal distribution with mean mu and variance sigma squared divided by n. Okay? So again, the central limit theorem tells us about the distribution of this random variable x bar sub n. It says it's approximately normally distributed with this mean and with this variance. Okay? Now, the common distribution referred to here in the central limit theorem is what we call the population distribution, or the distribution of the population. The common mean is called the population mean, and the common variance is called the population variance. So informally, the central limit theorem says that this random variable x bar sub n is approximately normally distributed with mean mu, variance sigma squared over n, for n quote-unquote large enough, regardless of the population distribution. Population doesn't have to be normally distributed. It could have any distribution that we want. Central limit theorem tells us that the sample mean has an approximately normal distribution. Now, a rule of thumb for when n is large enough is that n is bigger than 30. And we're going to see this requirement, n bigger than 30, come up a lot later on in this book. And that's because the central limit theorem forms a foundation for a lot that we do later on in the book. Okay. Now, if the common distribution, or if the population distribution is normal, then n can be of any size. It could be 2, 3, 4, doesn't matter. And that's really what theorem 381 is saying. 381 is kind of a special case of the central limit theorem when the population distribution is normal. So if the population distribution is normal, then n can be of any size, and actually this is not an approximation. This is the exact distribution of the sample mean. But that only applies when the population is normally distributed. If the population is not normally distributed, and this is an approximate distribution. Okay. So to illustrate an application of the central limit theorem, suppose people at a certain movie theater wait a mean of 30 seconds with a variance of 5 squared, seconds squared, to buy tickets. Find the probability that the mean wait time of a group of 50 moviegoers is less than 28 seconds. Okay. And so whenever we see a problem that asks for a probability of a mean, that tells us we're dealing with the central limit theorem. So in mathematical notation, we want to find the probability that x bar sub 50 is less than 28. 50, that's our sample size, that's the value of n. We want to find the probability that the mean is less than 28. So our population mean is 30, and the population variance is 5 squared. Now, we're not told anything about the population distribution, but that doesn't matter. Central limit theorem does not require a certain population distribution. Okay. So the central limit theorem tells us 3 things about the distribution of this random variable x bar 50. First, the central limit theorem says that this random variable is approximately normally distributed. That means we're dealing with a bell curve to calculate its probability. Second, the mean of x bar sub 50 is 30, the population mean. And then third, the variance of x bar 50 is the population variance, 5 squared, divided by the sample size n, which is 50. We do that arithmetic, and that comes out to be 0.5. So this all boils down to a non-standard normal distribution problem. So to calculate the probability that we want, we're going to convert this number 28 over to a z-score by subtracting the mean and dividing by the standard deviation. And so notice that this is an approximation because the central limit theorem says that the x bar 50 is approximately normally distributed. And so we do that arithmetic, we get a z-score of negative 2.83, and we look up that probability from table C1, and there's our probability, 0.0023. So that's all there is to using the central limit theorem. It all boils down to a non-standard normal distribution problem.